put these conditions in a few different reactions. And again, I know we're going through this relatively fast, but hopefully we'll see that this makes sense. That's the goal. Now, the first one is, let's go back to acidic conditions. We have this aldehyde here, and we have acid in the presence of bromine. And what you would find is that you would halogenate, so introducing a halogen, bromine in this case, at the alpha carbon, the one next to the carbonyl group. However, what you also notice is that we get a mixture of stereoisomers. So we get both the S and the R stereoisomer here. So we need to come up with some mechanism that can explain how we alpha halogenate there, and also why we get the two different stereoisomers. So let's see if we can figure this out. So we draw it here. We're under acidic conditions. So the first thing we're going to do is protonate the carbonyl. Not acidic. There's no carbon there that's on the alpha carbon. You cannot have a resonance stabilized position there. So we have a hydrogen here, and we're going to collapse this down into one step. Sometimes you'll see it drawn like this as well. Let's go ahead and then take this proton off, but to keep with our positive formal charges, let's move these electrons here, and we're going to form the enol all in one step. Move those electrons up into the oxygen. I think someone has their microphone on. If you can mute it, if you would, please. So now we've generated our enol, and let's first of all just draw the product. Now, the key thing here is that this is going to be a nucleophile, and a carbon nucleophile. So that's what we're going to use to form the new bonds. So let's put bromine down here. Then we have a decent leaving group, a good leaving group, just like what we've done with other reactions where we used bromine. So now what we'll do is we're going to regenerate our carbonyl group. So move these electrons back down here. We're going to use the electrons in that carbon-carbon double bond as our nucleophile to form a bond with the bromine and kick out our leaving group. So now for our product, and this step is probably not so much going backwards, but the arrows here are not that important, not as important. What we've done now is we've reformed our carbon-oxygen double bond. So that's going to have a positive formal charge. And then the key thing was we're forming a bond between this carbon, the alpha carbon, and the bromine. What I'm going to do for a minute now is just assert that we'll end up having this on a wedge, like what we see. And for some reason, we're going to end up having the product on a dash. We'll draw both of them. And now to end up balancing the charge in the end, we'll regenerate our acid. So we can go ahead and deprotonate this group. And this will be the same for both. I'll put this down. Powell, I think you have your microphone on. If you don't mind muting, please. So plus, oops, on a dash. Oops. Okay, so now here in terms of the mechanism, we can actually use what we've already drawn to explain how we add the halogen. So we first deprotonated our protonated species to generate the enol. So here's our enol. Use a different color. Here's the enol. And then that actually acts as a nucleophile, attacking Br2, forming the new carbon-bromine bond, and halogenates. Now, the remaining thing to consider is why is it that we get this mixture of these stereoisomers. And this is a very important aspect of this enolates chemistry. One of the things to notice here is that this carbon that we start off with, let's put the two hydrogens in there, either this one here, the two alpha hydrogens, or this one where I only showed the one, those carbons are sp3 hybridized, tetrahedral. The enol form here, where you have the carbon-carbon double bond, this carbon is sp2 hybridized. Both of these carbons are. Oh, the enol, which means this is trigonal planar. So it's hard now, you can't see me just waving my arms around like I would try to do in front of the whiteboard. But if you imagine this enol being trigonal planar in the plane of the screen, the bromine that's being added could either be in the front or behind. And so that's going to actually give you the two different stereoisomers. And there's a 50-50 chance that the bromine will be attacked if the bromine is sitting on the front or from behind the enol. And then what you've done is you've regenerated, in this case, an sp3 hybridized carbon. So in the video, I talked about racemization, because you can imagine if these two hydrogens, if one of them was a hydrogen and one was something else, on the far left here, this would be a chiral center. And then as you deprotonate to generate the enol, you've lost your chirality, because you now have an sp2 hybridized carbon. And then once you use your enol to react, in this case to halogenate, then you regenerate or reform, put a chiral center, and that's what we've done here. We started out with a center that was not chiral, just to make it a little easier, but we introduced the chiral center, that's sp3. So that's a very important point, just to reiterate again. We start off with sp3, alpha to the carbonyl. The enol is sp2 hybridized, it's trigonal planar, so we've lost that stereochemical information. And then when we halogenate, in this particular case, we've regenerated an sp3 carbon, which is chiral here. All right, so that's really under acidic conditions. Now, if that's not enough, let's go to a little bit more complicated scenario. We're not going to consider stereochemistry at this point, but let's think about now 1b here. What if the ketone's not symmetric? So now we have a methyl group on one side. We're going to halogenate in the presence of acid, and there's actually going to be one major product. So if we were to carry out this reaction, let's just write the potential products to start with. So we could imagine putting the bromine on the carbon on the right, or you could put the bromine and the carbon on the left. And I'm ignoring stereochemistry here. If you can form isomers, you will. Now, actually, if we were to carry out this reaction and you were to look at the different products, you would see that this one is the major product, and this one is the minor product. So it looks like the bromine is on the more substituted carbon. So now we want to think about, why is that? And maybe we can explain it with some of the concepts that we've already seen. Well, let's write out this mechanism again. So we have that methyl group, and then under acidic conditions, first thing we're going to do is protonate the carbonyl. See if I can manage space here appropriately. So we have this species here. Now we have a choice of removing a proton on either one of the sides. No double bonds in this case, Kyle. So this one will be a cyclo. It's a methyl cyclohexanol, 2-methyl cyclohexanol. You want to go back to the aromatic chemistry, which I understand because of how the excitement there, but here we're going to move away from the aromatics just for a couple of reactions. So why don't we, let's use a different color. Why don't we put a green hydrogen in here, and maybe like a purple hydrogen over here. See if we can make this really confusing. So now what we could do is take either one of these protons off. So if we were to take off the green one, we'll just stick with the green, I guess, here. We'll end up with this enol. If we were to take the purple proton off, this is really messy with those arrows in the middle. We'll end up with this enol. Now, in each of these cases, then, we can add bromine, just like what we saw in the previous reaction. I'll just stick with the green. Oops, to not have too many colors. It'll have a positive charge, which will get deprotonated. And then the other one. This is going to have to work its way over here. To form this species, which eventually will get deprotonated. Now, above here in this really kind of messy description, we said that the green product actually is the major product. And this really comes back now to the idea of a kinetic and thermodynamic product. So we have this under acidic conditions. On the far left, I wrote the protonation of the carbonyl group as being in equilibrium. And actually, all of these steps here initially are going to be in equilibrium. And the slow step overall is forming the enol. We're actually going from this stable carbonyl group on the left, we're protonating it under these acidic conditions, and then actually going from this keto form, which I'm trying to circle here, to the enol form is going to be energetically uphill. So that's going to be the slow step. So slow step, as well as for the purple one, the slow step. So what that means is that we have time for this to equilibrate. So our major product is going to go through the lower energy, want to form the more stable species, I should say, the more stable intermediate. And it goes back to organic 1 issues where we look at this alkene here. Notice this is a tri-alkyl substituted alkene and the hydroxyl group. So methyl, this carbon, and a hydroxyl. The purple alkene is only di-alkyl substituted. So remember with the alkenes, more substituted is more stable. So this one here, try to squeeze in one more thing with the green, is the more stable intermediate. It's supposed to say intermediate. Oh, thanks, Brian. Yeah, it looks like stop, doesn't it? Probably did. Looks like I did write stop. Slow. Oh, yeah, it does say stop. I'll write it slowly. Oh, no, see then the letters. Slow. Okay. So the key thing here when thinking about this, let's go back a couple steps. Now, if we have this asymmetric ketone up here in the left part, and the halogenation reaction occurs, we can put a bromo substituent at the alpha position. Now we have two possibilities. It can either be on the more substituted or the less substituted carbon. The observation is that the more substituted carbon is the one that has the bromo, that's like the major product. We're ignoring stereochemistry. Why is that? We can think about the mechanism, which is the same mechanism that we drew before, but now we protonate. We have two protons to take off, the green one or the purple one. And this is the rate limiting step. This is the energetically uphill step, and this is under equilibrium conditions. So the predominant pathway is going to form the more stable enol. So we're interconverting, occasionally forming this enol is going back, occasionally forming this one, but this is the more stable species under all these equilibrium conditions. So then, and the reason it's more stable is because it's the more substituted alkene, which then can act as a nucleophile and add the bromine. So it's the thermodynamic product. So I'm hoping that we're seeing how a lot of the other concepts that we've seen before actually we can revisit here.